squirrel cage motors feature a cylindrical rotor with evenly spaced slots housing copper or aluminum bars. These bars are short-circuited at both ends, forming a cage-like structure. The operation of a squirrel cage motor involves the stator creating a rotating magnetic field. This field induces currents in the rotor bars, causing the rotor to rotate. Squirrel cage motors are characterized by high starting torque, low starting current, high efficiency, and constant speed. They are also relatively easy to maintain. Wound rotor motors, on the other hand, have a cylindrical rotor with coils of insulated wire wound into slots. These coils are connected to slip rings which make electrical contact with brushes on the stator. In a wound rotor motor, the stator also creates a rotating magnetic field, inducing currents in the rotor coils, causing them to rotate. The key difference is that the slip rings allow the rotor coils to be connected to an external resistor. This allows for variable speed control by adjusting the external resistance. Wound rotor motors are characterized by variable speed capabilities, high starting torque, high starting current, and lower efficiency compared to squirrel cage motors. They also require more maintenance. For example, a single-phase exhaust fan with a full load current greater than 16 amps is likely driven by a squirrel cage motor. This is due to the squirrel cage motor's high starting torque and relatively low starting current characteristics, which are suitable for starting the fan. In contrast, a large industrial motor used to drive a variable speed pump might be a wound rotor motor. This type of motor is chosen when variable speed is needed to adjust the flow rate of the pump. The ability to control the speed of the motor by adjusting the external resistance connected to the rotor is a key advantage in such applications. The choice between a squirrel cage and a wound rotor motor depends heavily on the specific application requirements. If constant speed and high efficiency are primary concerns, a squirrel cage motor is often the better choice. If variable speed is required, a wound rotor motor provides the necessary control. When sizing short circuit and ground fault protection for motors, understanding the motor type is crucial. Firstly, consider the full load current, or FLC, of the motor. This information is typically found on the motor's nameplate. Secondly, refer to the National Electrical Code, or NEC, for guidance on overcurrent protection. NEC Table 430.52 provides guidance for selecting the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. This table specifies different percentages of the motor's FLC based on the type of protective device used, such as inverse time circuit breakers, fuses, or instantaneous trip circuit breakers. For example, if using an inverse time circuit breaker, the NEC typically allows a maximum rating of 250% of the motor's FLC for squirrel cage motors. However, this percentage may vary depending on the specific motor characteristics and application. For wound rotor motors, the percentage may be different. The code also specifies requirements for ground fault protection, which is designed to protect against ground faults that can occur within the motor or its associated circuitry. Ground fault protection typically involves using a ground fault relay or a ground fault circuit interrupter to detect ground faults and trip the circuit breaker. When selecting overcurrent protection for a motor, it is important to consider the motor's starting current, which can be significantly higher than the FLC. This inrush current can cause nuisance tripping of the overcurrent protection device if it is not properly sized. The NEC allows for higher overcurrent protection ratings to accommodate the motor's starting current, but it is important to ensure that the protection device is still capable of providing adequate protection against short circuits and ground faults. It is also crucial to consider the ambient temperature in which the motor is operating. High ambient temperatures can affect the motor's insulation and reduce its lifespan. The NEC provides guidance on directing motor conductors and overcurrent protection devices in high ambient temperature environments. In addition to the NEC, other industry standards and guidelines may provide further information on motor protection. These standards may address specific types of motors or applications. For example, standards from organizations such as the National Electrical Manufacturers Association, or NEMA, can provide guidance on motor performance, dimensions, and other characteristics. When in doubt, it is always best to consult with a qualified electrical engineer or motor specialist to ensure that the motor is properly protected. Understanding the differences between squirrel cage and wound rotor motors is essential for electrical engineers involved in motor selection, application, and protection. Knowing the characteristics of each motor type allows for informed decisions regarding motor sizing, overcurrent protection, and ground fault protection. Remember that squirrel cage motors are generally simpler, more efficient, and easier to maintain, making them suitable for a wide range of applications where constant speed is required. Wound rotor motors, on the other hand, offer the advantage of variable speed control, making them ideal for applications where speed adjustment is necessary. When selecting a motor for a specific application, consider the following factors. Firstly, the load requirements, including the torque and speed needed to drive the load. Secondly, the duty cycle, which refers to the pattern of operation, such as continuous or intermittent. Thirdly, the environmental conditions, including the ambient temperature, humidity, and presence of any corrosive substances. Fourthly, the power supply characteristics, including the voltage, frequency, and available fault current. Fifthly, the costs, including the initial purchase price, installation costs, and operating costs. And sixthly, the maintenance requirements, including the frequency and complexity of maintenance tasks. By carefully considering these factors, you can select the motor that is best suited for your application, ensuring reliable and efficient operation. Motors are typically protected against overloads by thermal overload relays or electronic motor protection relays. These devices monitor the motor's current and temperature and trip the circuit breaker if the motor is overloaded. The overload protection should be sized to protect the motor from overheating due to prolonged overloads, while still allowing the motor to start and run under normal conditions. Short circuit protection is typically provided by fuses or circuit breakers. These devices are designed to quickly interrupt the circuit in the event of a short circuit, preventing damage to the motor and other equipment. The short circuit protection should be sized to protect the motor from damage due to high fault currents. Ground fault protection is typically provided by ground fault relays or ground fault circuit interrupters, also known as GFCIs. These devices detect ground faults and trip the circuit breaker, preventing electric shock hazards and equipment damage. The ground fault protection should be sensitive enough to detect low-level ground faults, but not so sensitive that it causes nuisance tripping. Proper motor protection is essential for ensuring the safety and reliability of electrical systems. By understanding the different types of motor protection and how to apply them, electrical engineers can protect motors from damage and prevent electrical hazards. Always consult the NEC and other relevant standards for guidance on motor protection. Motor nameplates provide valuable information about the motor's characteristics, including the full load amps, voltage, horsepower, speed, and service factor. This information is essential for selecting the correct motor protection and conductors. The service factor is a multiplier that indicates the amount of overload the motor can withstand for a short period of time. For example, a motor with a service factor of 1.15 can operate at 115% of its rated horsepower for a limited time. When selecting motor conductors, it is important to consider the motor's full load amps and the ambient temperature. The conductors must be sized to carry the motor's full load amps continuously without overheating. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and ambient temperature. When installing motors, it is important to follow all applicable codes and standards. This includes proper grounding, wiring, and mounting. Motors should be installed in a location that is clean, dry, and well ventilated. Proper ventilation is essential for preventing overheating. Motors should also be protected from physical damage. Regular maintenance is essential for ensuring the long-term reliability of motors. This includes lubricating bearings, cleaning windings, and inspecting for wear and tear. Motors should be inspected regularly for signs of overheating, vibration, and unusual noise. Any problems should be addressed promptly to prevent further damage. When troubleshooting motor problems, it is important to follow a systematic approach. This includes checking the power supply, motor connections, and motor windings. A multimeter can be used to measure voltage, current, and resistance. An insulation tester, also known as a megameter, can be used to test the insulation resistance of the motor windings. If the motor windings are shorted or grounded, the motor will need to be repaired or replaced. Motor control centers, or MCCs, are commonly used to house motor starters, overcurrent protection devices, and other motor control equipment. MCC provide a centralized location for controlling and protecting motors. MCC should be installed in a location that is clean, dry, and well ventilated. Variable frequency drives, or VFDs, are used to control the speed of AC motors. VFD can save energy by reducing the motor speed when the load is light. VFD can also improve motor performance by providing smooth starting and stopping. When using VFD, it is important to use motor insulation that is rated for the high voltage spikes that can be generated by the VFD. Line reactors or filters can be used to reduce these voltage spikes and protect the motor insulation. Synchronous motors are another type of AC motor. Synchronous motors operate at a constant speed that is determined by the frequency of the power supply. Synchronous motors are often used in applications where precise speed control is required. Direct current, or DC, motors are another type of motor. DC motors are often used in applications where variable speed is required. DC motors require a DC power supply, which can be obtained from a rectifier or a DC generator. Brushless DC motors are a type of DC motor that does not have brushes. Brushless DC motors are more efficient and require less maintenance than brushed DC motors. Stepper motors are a type of motor that rotates in discrete steps. Stepper motors are often used in applications where precise positioning is required, such as in CNC machines and robotics. Servo motors are a type of motor that is used in closed-loop control systems. Servo motors are used to precisely control the position, velocity, or torque of a load. Gearboxes are used to reduce the speed and increase the torque of a motor. Gearboxes are often used in applications where a high torque is required at a low speed. Brakes are used to stop or hold a motor. Brakes are often used in applications where safety is a concern. Clutches are used to connect or disconnect a motor from a load. Clutches are often used in applications where the motor needs to be started or stopped without stopping the load. Motor bearings are used to support the motor shaft. Motor bearings should be lubricated regularly to prevent wear and tear. Motor windings are the coils of wire that carry the current that creates the magnetic field that drives the motor. Motor windings should be inspected regularly for signs of overheating or damage. Motor insulation is used to insulate the motor windings from each other and from the motor frame. Motor insulation should be inspected regularly for signs of cracking or deterioration. Motor cooling fans are used to cool the motor windings. Motor cooling fans should be kept clean and free of debris to ensure proper cooling.